So now we are seeing about population growth. The size of a population for any species is not a static parameter. It keeps changing with time, depending on various factors including food availability, predation pressure, and adverse weather. So, what are the factors that are determining the size of a population? Food availability, predation pressure, and adverse weather. In fact, it is these changes in the population density that gives us some idea of what is happening to the population, whether it's flourishing or it is declining. Whatever might be the ultimate reasons, the density of a population in a given habitat during a period fluctuates due to changes in four basic processes. Okay, two of which, natality and immigration, contribute to an increase in the population density, and two, mortality and emigration to a decrease in the population density. So natality refers to the number of births given natality refers to the number of births during a given period in the population that are added to the initial density. Mortality is the number of deaths in the population during a given period. So, natality refers to the number of births during a given period in the population that are added to the initial density. Mortality refers to the number of deaths in the population during a given period. Immigration is the number of individuals of the same species that have come into the habitat from elsewhere during the time period under consideration. Emigration is the number of individuals of the population who have left the habitat and gone elsewhere during the time period under consideration. So now we will be seeing the small table, this figure, where we have a proper thing. Okay, so natality, immigration, they add. Mortality and emigration, they subtract. Okay, that's the basic thing. So we know N defines, capital N is the population density. Now, so if the population density time t, then the density at time t plus is the following. Right? So you can, this is a very relatable graph, very relatable formula, because we have the population density in a given time period, which is equal to in t plus 1 is equal to n t plus this subtract this. Okay, that's all. That's what you require, right? So immigration I, natality B. Remember, natality is B. Mortality is D, emigration is E. Emigration, their respective letters. Natality is B, whereas mortality is D. That is very important to remember. So you can see from the above equation that the population natality is B, mortality is D. You can see from the above equation that population density will increase if the number of births plus the number of from the above equation that population density will increase if the number of births plus the number of immigrants is more than the number of deaths plus the number of immigrants, D plus E. B plus I. Under normal conditions, births and deaths are the most important factors influencing population density. The other two factors assuming importance only under special conditions. For instance, if a new habitat is being colonized, immigration may contribute more significantly to population growth than birth rates. Growth models. Does the growth of a population with time show any specific and predictable pattern? We have been concerned about unbridled human population growth and problems created by it in our country, and it is therefore natural for us to be curious if different animal population in nature behave the same way or show some restraints on growth. Perhaps we can learn a lesson or two from nature on how to control population growth. So, does the growth of a population with time show any specific and predictable pattern? We have been concerned about the unbridled um, human population growth and problems created by in our country, and therefore natural for us to be curious if different animal population in nature behave the same way or show some restraints in the growth. Perhaps we can learn a lesson or two from the nature on how to control the population growth. So we're just checking out how the growth of in different species are. It is basically natural to find that. Okay. So we have found out the four. Until now, what we have done, we have found out what can determine the size of a population. Then we termed four terms, and then we found out a formula. Then we saw the growth model, how the growth of a population with time is specific and a predictable pattern. And we were asking questions, and it is definitely we are going to be seeing about the exponential growth and logistic growth. Definitely it is going to be natural to ask such questions. So first of all, exponential growth, resource, food and space availability is obviously essential for the unimpeded growth of a population. Ideally, when resources in the habitat are unlimited, each species has the ability to realize fully its innate potential to grow in numbers. So, when they're unlimited, the species, they realize their full potential to grow. So, Darwin, as Darwin observed while developing his theory of natural selection. So, then the population grows in an exponential or geometric fashion. Before that, I want to Darwin is very important. Okay, so examples, formulas and scientist names will be highlighted in the orange color. Now coming back over here, this is my exponential growth part, right? So we're learning about exponential growth. So please follow me. So geometric fraction. In a population size n, the birth rates, not total number, but per capita births are represented as B, and death rates again per capita death rates as D. Then the increase or decrease in n during a unit time period T will be n differentiation of n. D by dt n will be D by dt n is equal to B minus D into n. What does B refer to? It refers to the natality, and D refers to the mortality. Okay, so B minus D is equal to R. What is R? Darwin's fitness, right? So differentiation of the population density is, so the population density with respect to time is the population density into natality into the difference between natality and mortality. Okay, so basically we have this equation, very important equation. Okay, so the R in this equation is the intrinsic rate of natural increase. So it's basically Darwin's fitness, right? So as it is very important parameter for chosen for assessing impact of any biotic or abiotic factor on population growth. To give you some idea about the magnitude of R values for the Norway rat, the R is 0.01. Okay, Norway rat, such a one, flower beetle, greater. In 1981, the R value for human population in India was 0.0205. Find out the current R value. For calculating it, you need to know the birth and death rates. Okay. So now the above equation describes the exponential or geometric growth population of a pattern of a population, and the result is a J-shaped curve. Okay, so today we had a question where they asked the exponential or geometric growth. What is the exponential growth? What graph is given? So basically it's a J-shaped curve. When we plot n in relation to time, if you are familiar with the basic calculus, you can derive the integral form of the exponential growth equation as the following. Okay, so I think this is a very obvious equation kind of. You see any exponential, it will be such a equation, right? So we know population density after time t, population at time 0, intrinsic rate of natural increase, the base of natural logarithm, which is 2.71, and decimals. Any specific growing exponentially under any species growing exponentially under unlimited resource condition can reach an enormous population density in a short time. This is what Darwin was telling. So Darwin showed how even a slow growing animal like elephant could reach enormous numbers in the absence of checks. So the following is an anecdote popularly narrated to demonstrate dramatically how fast a I'm sorry, I was reading without just showing you guys, right? So let me read it once more. So, any species growing exponentially under the unlimited resource conditions can reach enormous population density in a short time. Darwin showed how even a slow growing animal like the elephant could reach enormous numbers in the absence of checks. The following is an anecdote popularly narrated to demonstrate dramatically how fast a huge population could build up and growing exponentially. Okay, so we're going to see the anecdote. Before that, let's just see the graph. This is our J-shaped graph. Where is our J-shaped graph? This is our J-shaped graph. This is the exponential growth, right? This is the exponential growth. We can see K over here. Okay, K, we will come back to that. This is N, this is R, this is differentiation of N. So now, population growth curve A when responses are not limiting the growth, plot is exponential. So A when responses are not limiting the growth. Okay, so this is like exponential growth. There's no checks. Okay, now we'll come back to B when we are learning about logistic growth. So I have to read the anecdote as I had mentioned earlier. So now the king and the minister sat for a chess game. The king, confident of winning the game, was ready to accept any bet proposed by the minister. The minister humbly said that if he won, he wanted only some wheat grains, the quantity of which is to be calculated by placing on the chessboard 1 grain in square 1, then 2 in square 2, then 4 in square 3. So this was one thing that I did in my 8th grade. We made a story plot based on this. Okay, so it was very fun, but unfortunately we couldn't do it on the math day. So 8th grade I knew the story. So we were working on this. I had to make the script and all those, but yeah. Okay, so I know the story, though I have not read this before in this textbook. Okay, so 2 in square 2, then 4 in square 3, then 8 in square 4, and so on, doubling each time the previous quantity of wheat on the next square until all the 64 squares were filled. The king accepted the seemingly silly bet and started the game. Okay, but unluckily for him, the minister won. The king felt that fulfilling the minister's bet was so easy. He started with a single grain on the first square and proceeded to fill with the other squares following the minister suggested the procedure, but by the time he covered half the chessboard, the king realized to his dismay that all the wheat produced in his entire kingdom pooled together would still be inadequate to cover all the 64 squares. Now think of a tiny paramecium starting with just one individual and through binary fission doubling in size every day, and imagine what a mind-boggling population size it would reach in 64 days provided food and space remain unlimited. So it is an excellent example, right? So I remember how they used to take sacks and sacks to, it was a story, okay, it was I also saw it in an animated form. So yes, we'll come back to that. It's an unwanted thing right now, right? Okay, so now logistic growth. No population of any species in nature has its disposal unlimited resources to permit exponential growth. So no population of any species in nature has its disposal unlimited resources to permit exponential growth. This leads to competition between individuals for limited resources. Eventually the fittest individual, just a minute. So this leads to the competition between the individuals for limited resources. What? That there's no exponential growth and there's a lot of checks. So there's the eventually competition. Eventually the fittest individual would survive and reproduce. The governments of many countries have also realized this fact and introduced various restraints with a view to limit human population growth. In nature, a given habitat has enough resources to support a maximum possible number, beyond which no further growth is possible. Let us call this limit as nature's carrying capacity, K, right? For that species in that habitat. Excellent. Okay, basically carrying capacity. A population growth in a habitat with limited resources show initially a lag phase. Okay, it's followed by phases of acceleration and deceleration, and finally an asymptote. Okay, let me find out what that is. Okay, and I will come back to you before the previous one. When the population density reaches the carrying capacity. So a plot n in relation to time t results in sigmoid curve. This type of population growth is called Verhulst-Pearl logistic growth. Over there, Darwin was the one. Here it is Verhulst-Pearl. Okay, and it is described by the following equation, right? So this is an excellent equation, again differential form, and what we find out is Rn into k minus n into the, what is k? Carrying capacity. Okay, so since resources for growth for most animal populations are finite and becoming limited sooner or later, the logistic growth model is considered a more realistic one. Gather from government census data the population figures for India for the last 100 years, plot them and check which growth pattern is evident. So we'll do this later. Okay, I don't think so I'll be able to do it first of all. Okay, please you have to do it. Okay, logistic growth is more realistic. Okay, in the next session we will be learning about life history variation, and then we will move on to population interaction. Okay, population interaction is a very big topic, very big topic. Okay.